Here is another population model that takes into account competition for limited resources, and this is the so-called logistic model. So the logistic model is very similar to the Malthusian growth model, but it has an extra factor in here. So we still have dp dt equals negative a times p, and so that's kind of the k times p that we saw in the other model. But now the extra factor that we have here is that p times, or that p minus p1. That's an extra factor, and p1 is the carrying capacity. And that basically accounts for the fact that if there's only limited resources and there's too much population, there's not going to be enough resources for the population. Think of there's too many rabbits and not enough food. And so what happens is that the population will decrease then. So think about it. If P is greater than P1, this is positive, this is negative. So if this is in total negative, that means that dp dt is negative, and that means that the population is decreasing. There are two equilibrium solutions or constant solutions to this differential equation, namely p of t equals 0. So if you start at the population 0, it cannot grow. And the other one is if p of t is p1 equal to the carrying capacity. Notice that when you plug in p1, this becomes 0, and that means dp dt is 0, and that means p is constant, and so p1 is a solution. So there are basically two cases to consider of what the population growth looks like. If p naught is less than p1 and greater than 0, the population will increase fast at first, and then it will slow down until it reaches the carrying capacity or the equilibrium solution. If the starting population p naught is greater than p1, then as we discussed before, this is going to be positive, and then with a negative in front, that's going to be negative, and so the population will decrease until it reaches the carrying capacity. Now, I will not show that in this video, but this is still a separable equation, right? The right-hand side does not depend on p, so we can put all of this on the other side, bring the dt on the other side, and then integrate both sides. If you do that, you can show that the general solution of this model is p of t is p naught times p1 over p naught plus p1 minus p naught times e to the power negative a times p1t. And so if t goes to infinity, so let's just briefly look at what happens to this model when t goes to infinity. So if t goes to infinity, then this term goes to 0. And so this whole denominator here goes to p naught. This is a constant p naught p1. So if t goes to infinity, we actually see that p of t goes to p naught over p1 over p naught plus 0, right, which simplifies to p1. So we see that t goes to infinity implies that the population will reach that equilibrium solution.